afternoon session. Our first speaker is Dan Halpern-Leisnter, and he's going to tell us about modular objects in digit categories.
Okay, thank you very much for the invitation. And does Maxine here? I don't know. Well, anyway, happy birthday. And thank you for many years of inspiring mathematics. So I'm trying to give something, basically every aspect of this talk is going to be inspired by Concevich's work. So my goals are going to be, so first of all, I'd like to discuss a framework for studying moduli problems in algebraic geometry. And then I'd like to apply this framework for the moduli objects in DG categories. And then at the end, I'd like to discuss a little bit of the implications for homological mirror symmetry. I'm not necessarily going to go through in this order. It's all going to be kind of mixed around. Actually, do you think there's some way to get this to stay open? So I'm having some trouble scrolling through here. Oh, okay, fine. So, okay. Anyway, so this is a kind of cartoonish dream version of the homological mirror symmetry conjecture. It basically says that for any Calabi-Yau manifold, and maybe any should have a question mark, there's a mirror Calabi-Yau manifold such that the Fukaya category of one is equivalent to the derived category of coherent sheaves of the other. And so, this was proposed a long time ago, and as a sort of, inspired by physics without any actual description of what the mirror might be. And so there have been a series of constructions over the years, and that's actually been a big part of the subject, is trying to make sense of what this means by saying, what is the mirror? So the first construction is this SYZ mirror symmetry, and that was shortly after the original conjecture by Concevic. And basically it's that there should be a Lagrangian torus vibration, a special Lagrangian torus vibration on the original Calabi-Yau, and then the mirror manifold is you take a fiber-wise dual of those tori. So let's go to SYZ. It's a very well-known proposal for construction. More recently, there's been another approach to constructing mirrors, and both by Milano and by Gross-Siebert. They have come at it from different perspectives, but basically the idea is there's some kind of tautological mirror symmetry. If you have the symplectic manifold, then the symplectic homology or something like that is going to act on the Fukaya category, and so you have a functor, and naturally you have a functor from the Fukaya category of M to some category of modules over some ring. And this works very nicely in these kind of non-compact situation. And there's a model maybe for how to do it in the compact situation too, Dan assures me. So this is a more recent idea. And then there was, around the same time, there's this proposal by Tohen and Vacquier that maybe you could construct a mirror as a moduli space of objects in the Fukaya category. It's kind of a version of one. It's like sort of a slightly different formulation of one, because these special Lagrangian tori are objects in the Fukaya category. And so Tohen and Vacquier had some work saying, well, what would it mean to have a collection of objects, and that would get, where you have a moduli space and you get an equivalent. So basically the question, how do you recognize when your category is equivalent to the derived category of variety? And their results had lots of assumptions, basically. So I would say that of these three proposals, the first two are highly developed, or more developed. Basically, this ongoing work. They both encounter certain difficulties. So namely, it's hard to construct special Lagrangian fibrations. I mean, it wasn't even known until fairly recently that there is a special Lagrangian torus in the quintic. So constructing, and also when I say compactifying the mirror, you have to also say what kind of singular Lagrangians are you going to allow, because the moduli of just special Lagrangian, embedded special Lagrangian tori is not compact. So that's a subtlety there that makes it a challenging approach. And then for 2, one of the challenges is that you get something like an affine variety, or maybe a homogeneous coordinate ring of a mirror. You can construct that from the enumerative invariance of the original manifold, but that thing might be singular. And so there's some question of, it doesn't quite get you all the way to a commutative, variety that you're equivalent to. So, but today I'm going to talk about the third approach, and I'm going to try to develop it a little bit more, make it a little bit more precise, using the theory of stability conditions. So that's the context. Okay. So what is non-commutative algebraic geometry? I'm going to work over a field of characteristic 0. And so the general kind of yoga of this field is to think of a smooth and proper DG category just as the space.
Okay, maybe just something.
Oh, really?
Yeah.
I'm sorry. Oh, I'm really sorry. Yeah. Okay. Yeah. If Jan's not here, but if he's watching, I apologize. Yeah. All right. Yeah. And so Tohen and Vake actually show that when you have a smooth and proper category like this, it's actually equivalent to the category of perfect DG modules over some DG algebra. And the conditions on the algebra are relatively concrete. So I like this formulation because everything is relatively simple, and you can forget the letters DG, and you're just thinking about modules over an algebra. It's relatively concrete. But the amazing thing about this perspective is that it includes, oh, I forgot. So the definition of perf of A, for those who aren't familiar, is just the smallest thick triangulated subcategory that contains A inside the category of all DG modules. So even though it's a relatively tame looking object, it's just modules over some algebra, some finite dimensional DG algebra, it includes basically all of algebraic geometry, because DB co of a smooth proper variety always fits into this framework. I guess smooth, is it for proper or projective? Anyway, a smooth projective variety. Proper is fine, yeah? Okay. So a smooth proper variety fits into this framework. Also Deligne-Mumford stacks and the kinds of things that people study in traditional non-commutative algebra, finite modules over a finite dimensional algebra, finite global dimension. This is also fits into this framework. So the original kind of, earlier kinds of non-commutative algebra questions also fit into this framework. And also, of course, the very exciting thing from this perspective is that the Fukaya category, so symplectic topology, also produces non-commutative spaces. So it's a very flexible framework, and that's the framework I'm gonna work in. So I mentioned I want to say a little bit about some kind of generalities or general techniques, because this audience maybe is not necessarily checking in with what's going on in algebraic geometry. So, and there's been a lot of progress on some of these general methods for analyzing moduli problems in algebraic geometry. So sometimes I'm going to talk a little bit generally. And so the way algebraic geometers talk about a moduli problem is they just define a stack. And this perspective goes back to Grothendieck, and you say this is the stack that classifies families of objects in whatever moduli problem you're thinking of. So it's just a functor from K-algebras to groupoids that satisfies some descent conditions. Okay, so a derived stack is basically the same thing, except instead of eating rings, it eats commutative differential graded algebras, and instead of spitting out groupoids, it spits out infinity groupoids, which are just spaces or Kahn complexes. And then there's this definition of what this is just a kind of a sheaf, an arbitrary sheaf. So what does it really mean to be geometric? And there are slightly different ways to do this, slightly different definitions, which give you different concepts, but this is a very clean one, where you say a stack is, so this is a derived stack is n-geometric and finally presented. That's what FP stands for. if there's a cover by an affine thing, a finite presentation, and such that the fiber product is n-1 geometric and finitely presented. So it's an inductive definition. And so, for classical algebraic geometers, for people, I don't know what classical means, but for algebraic geometers, this can be a little bit hard to get intuition for what is, a 15 geometric stack or something like that. So most algebraic geometry takes place in the world of, in this context, one geometric stacks, which is just a stack that admits a cover from an affine scheme and whose diagonal is also affine. So that would be one geometric. And sometimes they just call that geometric. Yeah, so the inductive thing starts with a zero geometric thing is just affine. So by this definition, a one geometric thing is just like, a quasi-compact stack with affine diagonal. And a quasi-compact algebraic stack with affine diagonal. So the moduli functor that I'm going to be talking about today is this functor that was studied by Toon and Vaquier. So basically, you can consider the value for K algebras, or more generally for commutative differential graded algebras, and this is just what it is. It's just the functor that takes a ring R to the objects in this tensor product, perfect modules over this tensor product algebra. And you think of this as a family of objects over R. And when I say that little isomorphism subscript, I said it should go to groupoids. So I take this category and I just take the subcategory that just only keeps isomorphisms. Or technically, it's like the largest Kahn subcomplex of the quasi-category. Okay, so the theorem, which is a remarkable theorem, is that this thing, at least locally, is an n-geometric finally presented stack. So intuitively, this kind of you might expect this because, well, at least based on, this uses the Toon-Vaquier result that the category is equivalent to the category of modules. But classically, if you consider finitely generated modules over a finite dimensional algebra, that's very clearly an algebraic stack. It's just a vector space, and then there's some, you have to say what the generators do, something like that. So this is a kind of derived version of that. Yeah.
So what is this A dot?
A dot, oh, sorry. Sometimes I put the dot there and sometimes I don't. A is the CDGA. Oh, no, A is the DGA.
A is R.
No, A is the DGA. Oh, sorry. A is the thing that the category is equivalent to A modules.
Oh, okay.
Yeah, that's the A dot. C is equivalent to perf of A dot.
Okay.
Yeah, I will not include the dot later on just because I got a little lazy. Okay, so this is this stack, but as I mentioned, it's a higher derived stack, and so not a lot of the techniques of algebraic geometry don't apply. So the key to cutting it down to something that algebraic geometers can think about is called a T-structure. Basically, it's a pair of subcategories like this, satisfying some axioms. So basically, well, these are the axioms. So you can shifting to the left. So you take these what are called connective complexes, connective objects. As you shift them to the left, they're still connective. And there's a semi-orthogonality between these two subcategories. And then there's the existence of an exact triangle. And the example you should keep in mind is just what I say about down here. The standard, if you just have a ring, the standard T structure, then this C greater than 0 consists of the complexes who only have homology in positive homological degrees. And this category, the intersection of C greater than -1, C less than or equals 0 is called the heart. So using a T structure, we will cut this. I mean, it's beautiful, the fact that it's algebraic in some sense, but it's also this wild thing. So we'll cut it down to a 1 stack in the following way. We equip C with a T structure. And then there's some kind of formal mechanism. If you have a T structure on perf of A, you get a T structure on the perf of R tensor A, and it's defined this way. But the key is that, I mean, the key subtlety about this is that you get a T structure in the big category of all modules. This is some like super general kind of construction, and these connective objects are generated under extensions and colimits by just the base change of C greater than 0.
So the CTJ is non-positive with this?
No.
Both.
Both, yeah. Well, the key is you start with the T structure. So you start with some arbitrary T structure on perfect A. And then you just define this new T structure on the base change by saying
A is a constant, A is K, yeah.
Yeah.
What will be T structure of modules for?
Wait,
No.
yeah, you're right. You do need no, it's okay, because K is a field. That's a
K is
fine.
field, A is K, but R is goes in both directions. You don't see any.
No, R is, the CDGA, yeah. CDGA, yeah, R should be connective.
It goes to negative.
Yeah, it just goes to the negative, yeah. Okay, so using this T structure, actually, so using this T structure, you can define a subfunctor like this. And basically, this is the analog of what we think of as flat families. So you start by saying, what is a family of objects? But maybe that's not yet the right moduli functor. So basically, you say that the E, you consider objects such that after arbitrary base change, they lie in the heart of this induced T structure. And this automatically cuts you down to a one stack. So if you have a K algebra that's not a CGA, it just concentrated in degree 0, then this is an actual groupoid. I mean, it's infinity groupoid with no higher homotopy groups. And so now you can think of this as a stack in the usual sense of algebraic geometry. And so the examples of these kinds of stacks that people think about, as I mentioned, it's representations of a finite dimensional algebra or flat families of coherent sheaves. So these are constructions. This is a general thing that recovers these constructions in specific examples. So, okay, that's fine. This is a moduli functor, and there's this philosophy that maybe you should stop there. But of course, that's not actually where the story ends. So most of the time when you write down one of these moduli functors, especially like coherent sheaves, that doesn't tell you very much. It doesn't give you very much geometric information. It doesn't give you geometry to play with. So ideally, you would want to have an algebraic stack that has a moduli space. And so there is an intrinsic notion of a moduli space in algebraic geometry, and this is the definition. It's actually very simple, but it hides a lot of interesting implications. So even though it has this simple definition that it's just a morphism to an algebraic space, so that the push forward is exact and the push forward of O is O, turns out that implies that it's universal for maps to algebraic spaces. So this is a moduli space in the sense it's the initial it's the initial object in the category of algebraic spaces that receive a map from X. And not only that, like recently, so this definition was introduced, but there weren't actually ways to construct it except for GIT. It was the definition was sort of inspired by GIT. So we knew that was the way to construct these moduli spaces. And then more recently, actually, they proved that every good moduli space, étal locally over X, is a GIT quotient. So étal locally over X, it turns out this simple definition says that kind of étal locally are GIT quotient. And this actually unlocked a perspective shift. So it's like, well, yeah, so that means that if you're trying to actually construct a moduli space, you basically are still always going to be doing GIT like this. And it basically led to this, to some work with myself and Halpern-Leisnter, where we managed to find criteria that are very relatively simple to check for an algebraic stack. In particular, they involve families over just surfaces. And they imply the existence of a moduli space just directly, intrinsically, without appealing to some GIT setup. A reductive Lie group, yeah. Yeah. So under the hood, you're sort of finding in a tall local cover of your stack by spec of R mod G, and the result told you that every construction of a moduli space has to somehow be that way. And this allowed us, that was the starting point for thinking about it, and we come up with these criteria. So, but the problem is that if you want to apply the criteria, you still need an algebraic stack that's like bounded, that's actually finite type. That was in the statement of the last of the, oh, wait, did I make a theorem? I didn't state a theorem, but it's implicit in these criteria require you to have a quasi-compact stack. So if you're only locally finite type, then you need a notion of semi-stability. And there is also a general framework for thinking about that. So basically, all examples of semi-stability in algebraic geometry, or many examples of semi-stability, I should say that, many examples of semi-stability in algebraic geometry, and conjecturally all examples of semi-stability in algebraic geometry sort of come from this thing. There's a numerical invariant, which is a function that takes a map from A1 mod GM to the stack and spits out a number, or maybe something more general than a number, maybe something in some totally ordered group or something like that. But and there are some hypotheses that I've omitted. So the example, if you take the stack of vector bundles on a Riemann surface, then a map from A1 mod GM to that stack, that moduli stack is just a filtration of vector bundles indexed by integers. And if you take the graded pieces, you have some number, this is the formula. And I just show this, it's not important for the discussion that follows, but just to give you some sense of what these functions look like. It's a function that's actually, the sort of algebrogeometric data is encoded in the ranks and the degrees, but as a function of the weights W, it's a sort of nice convex function. It's actually sort of a quadratic form. It's a linear form plus a positive definite quadratic form in W. So that's that, and if you have such a numerical invariant, you can do the following. You can say that a point, an object in your moduli problem is semi-stable if for any map that takes 1 to the original point x, this number is greater than or equal to 0. And an HN filtration is a filtration that minimizes this number. And so this is, this goes way back when I was in grad school, and I realized this, that it's just a very kind of, I still find it to be sort of remarkable that, so, the usual way you see HN filtration is described, it's a very categorical thing. So you find a maximal, subobject with maximal slope, and then you do an inductive procedure. But this is actually saying that among all filtrations and all possible weights, there's a unique filtration and a unique choice of weights that minimizes this nu.
Index rational numbers if you have integers. It's possible.
I give myself a little bit of leeway in talks to. So in general, these should be Q filtrations or R filtrations, and there's sort of ongoing work of making sense of that kind of thing in general. Okay, so this is the setup. So the codimension 2 filling conditions that I mentioned are the following. So I've realized I don't have a clock, which isn't always a problem. Okay. So the codimension 2 filling conditions, you can state it very succinctly by just saying, if you have sort of any algebraic surface with a non-trivial GM action, and you have an equivariant family over that surface away from a closed fixed point, then that a family extends uniquely and equivariantly over the fixed point. So there basically are 2 local models for this. One is like spec of a DVR times A1 mod GM, and the other one is like, it's like 2 axes meeting, but this
capital letter S looks like any surface or part of the domain S complete.
No. Sorry, that is a big mistake. Yeah. S is a surface. S complete is something else. S complete stands for Shishadri. So Yeah, so there's this little scheme, a little surface basically, which is, yeah, so, oh yeah, I have this thing, it's beautiful. So, there's this little stack, which is a surface, this kind of regular, two-dimensional scheme, and it has a single close point where S and T are both 0. And the GM action gives, S weight 1 and T weight -1. And we call this a Seshadri test scheme because this maps from the stack are sort of, if you remove the origin, if you remove 0, the stack is just 2 copies of spec of R, where R is a DVR. This is just 2 copies of spec of R glued at the generic point. And so if you wanted to test if a scheme is separated, basically what you're saying is that every map from 2 copies of the DVR that are glued along the generic point extends over this quotient stack STR bar. So S stands for Seshadri because these kinds of arguments sort of, it was inspired by stuff that appeared in his work, basically, for showing that moduli spaces are separated. So that's what S completeness is really. But you can just smush them together and just have this general definition. So now we have our situation. So suppose that you have some stack that's locally finally presented, one geometric, in other words, it lives in the world of actual, usual algebraic geometry, and it satisfies these codimension 2 filling conditions. And then in addition, it has a codimension 1 filling condition. So in other words, it satisfies the existence part of the valuative criterion for properness. So families extend families over punctured disks extend over the puncture. Then there are sort of necessary and sufficient conditions for everything to work nicely. So there's a HN boundedness condition, which I'm going to explain it a little bit later. So if you'll excuse me to just say that there is this HN boundedness condition, but if this condition is satisfied, then basically every point has a unique HN filtration. And if you stratify the stack by the type of the HN filtration, that gives you a locally close stratification of the stack. And in particular, the semi-stable points are the points whose HN filtration is trivial. So one of the strata in the stratification is the semi-stable locus, and that is an open substack. So openness of semi-stability is sometimes a hard thing to show. And then the second thing is if the semi-stable locus happens to be bounded, then it has a proper good moduli space. So basically, there's this setup where you have a maybe locally finally presented algebraic stack, and you have some data on it of a numerical invariant, and this gives you, turns out that these are sort of necessary and sufficient criteria for these structures to appear, this Hardy-Narasimhan stratification and the moduli space for the semi-stable locus. So that's basically the update on like the general approach to moduli problems like this in algebraic geometry. So now what I'm going to do is come back to Earth and the stuff that we were talking about. So we're now thinking about the specific moduli problem, which is objects, families in the heart of a T structure on perf of A for some DGA A. So I'm going to tell you what is stability conditions, although it's a little different than the original formulation of stability conditions due to Bridgeland. For some reason, for certain purposes, this was more convenient for us. So basically what I do is I fix a finite abelian group, and a finally generated free abelian group and a norm on it, and a locally constant map from M to lambda. And basically what this means is that if you have a family over some connected spec of R, then every fiber has the same value of lambda. So the example here is for dB of co, then V is usually just the Chern character, and lambda is just the image of the Chern character map in the cohomology that fits into this framework and some choice of norm. So in my reformulation of what is a stability condition, basically you have just 2 structures. We'll One is a collection of T structures indexed by real numbers. And the other is just a homomorphism from lambda to C. And the satisfy conditions. So the conditions are that, so first of all, this C greater than phi has to be a union of C greater than A for all the A less than phi. So in particular, C greater than phi 1 is contained in C greater than phi 2 if phi 1 is bigger than phi 2. So containment like this. So basically you think of this as a filtration of the category indexed by real numbers. And then you also want some boundedness condition. So basically E, any object of the category should lie in some finite window. And then there's this other condition. So so let me just say, so if what it says is that if you have a non-zero object in some small window, so they call this a narrow phase width. So if you have some object in CAB with the interval of size W less than 1, then you have this containment. So what this really means is that, let me get rid of this. Basically, it means that it means that Z of V lives in some cone like this, some cone that's shaped like this. So it's saying that, if your object lies in the phase interval A to B, then Z of it lies in some cone, and then Z of V divided by the norm of V is bounded away from the origin. And so this is sort of a combination of the support property and other properties you usually see for stability. This condition C is very different. But very importantly is that this condition doesn't require the existence of this definition does not require the existence of Halpern-Leisnter filtrations for people who are familiar with stability conditions. So this looks less scary to me than the usual definition. But it turns out it's equivalent. So if you have a stability condition of this kind, so central charge bounded in these sectors away from the origin, then you can define what is the maximum phase of an object, like I've done there. It's just how far can you bring it in on the right and bring it in on the left. So you get phi plus and phi minus. And then you can say that an object is semi-stable if phi plus is equal to phi minus. And the definition that I gave implies that every E has a Halpern-Leisnter filtration. So every E has a filtration like this with the graded piece semi-stable of phase phi I, such that the phases are decreasing. And then for any object, I define the mass to be the absolute value of the central charge of the graded pieces for this Halpern-Leisnter filtration. So for experts, as I mentioned, this structure here, just the T structures alone, plus a Noetherian hypothesis that actually is automatic in the context that I said. We call this a sluicing. And the reason why this was nice from a moduli perspective is that it enjoys nice base change properties. So basically, if you have a map that's a composition of polynomial algebras, localizations, and perfect algebras, then you can base change a sluicing. Oh, a polynomial like R goes to R joins T. S is perfect as an R module. Yeah. So yeah, so the general thing is general base change is hard to show actually. You can always base change a T structure to the category of modules, but the question here is when does that T structure preserve the category of perfect modules? And that's kind of a special thing. So let me tell you about the main theorem now. So I imagine we have a stability condition on the category, and we consider this inequality. So basically, there should be some constant such that for all modules, for all perfect modules, you have an inequality of this kind, where m is the mass function that I introduced on the last slide. And in fact, it actually suffices to just consider h naught of n. There are various different formulations. It's called the mass-Hom bound. It doesn't look like there's any Homs here, but in general, what you're bounding above is the Homs from E to F in terms of the mass of F. So if E is a generator, it becomes, so you can think of that homology as just the Homs from A to N. So the theorem is that if this holds, then you have the following. So fix a phase R, and I consider the T structure, which is just the corresponding to phase phi. So, so there, as we discussed before, this gives you a one stack, but it's not in general for a T structure. It's not clear that that stack is algebraic. But in this case, the mass-Hom inequality implies that this is an open substack, and therefore it's algebraic. And in fact, its diagonal is automatically affine. Also, the mass-Hom inequality implies that you have that M phi has a theta stratification by Halpern-Leisnter filtrations. There's a slight, it's not quite formulated the way the general thing is formulated. You have to tweak it a little bit, but basically this is what happens. You have a theta stratification by Halpern-Leisnter filtrations, and that if you bound the mass, you get a quasi-compact union, open union of strata. And then the final thing, which is kind of the most important, is that, so, in particular, this plane 2, I guess that should be less than or equal to, so if you fix a class V, and I say, when is the mass equal to the norm of Z of V, that's exactly telling you semistability. That's exactly the semistable locus. And so a sort of a corollary of 2 is that the semistable locus is open and bounded, and that it has a proper good moduli space. That follows from this general machinery.
Sorry, your contract is smooth proper category.
Smooth proper category. Yeah. Yes, then you have this. Yeah. I mean, I've not pushed to the limit in that direction. There might be other versions. Oh, in particular, one thing that I think is very interesting that we haven't thought about yet is what happens if you have a smooth category that's not proper. So these non-compact schemes or something that are still, then you should still be able to construct moduli spaces, but that's for another day. And then the comment is that condition 3, the existence of these moduli, the boundedness of the semistable locus for all V, actually implies it implies that the homology of M is bounded above by some function of the mass. So this is just saying that function should be a linear function. And so the key idea behind this theorem is boundedness. So that basically what I'd like you to take away from the general discussion of moduli problems is that there are now techniques that are in place to set up a moduli problem so that very nicely, so that you're going to have moduli spaces and Halpern-Leisnter filtrations and so forth, but it always comes down to boundedness. That's the only thing that we don't have a general approach to. Is showing the boundedness of the semistable locus and the HN boundedness. So one thing what you can think about is going on here behind the theorem is basically it's a new way of checking boundedness in this particular class of moduli problems. So just to make it more precise, basically, the stack is automatically, the stack of objects in the heart automatically has, is theta reductive and S complete. And so in this example, I told you I would tell you what HM boundedness is. Now I'm going to tell you. So what HM boundedness is here is the following claim, that if you have a bounded set of objects, then you can consider the Halpern-Leisnter filtration of each object in that bounded set of objects and the graded pieces. And even if when you do that, you still land in a bounded set of objects. So the set of objects that arise as associated graded for the Halpern-Leisnter of any E and S is also bounded. That's what HM boundedness is. And so the idea that behind this thing is that Tohen and Bacchier, when they prove this algebraicity, actually what they do is something a little bit more precise. There's a forgetful functor where you take an object in perf of R tensor A, and you just regard it as an object in perf of R. So perf with no decoration is sort of like analogous to the stack. I mean, it's the stack that takes any R to the category perf of R. And that morphism is quasi-compact. And what the Hom mass inequality does for you is it lets you say that the set of objects in the heart of the T structure with mass less than m is actually contained in the preimage of a bounded subset of perf, and hence it's also bounded by the Tohen-Bacchier theorem. And that it simultaneously implies the HM boundedness condition and the boundedness of the semistable locus. So that is the main theorem on the existence of moduli spaces for Bridgeland semistable objects in DG categories. I wanted to say a little bit, take a step back and say a little bit about the motivation, because it does rely on this inequality. And so I'm going to talk a little bit about the inequality and what we know about it. So it came from a totally different area. Basically, so the cool thing about the spaces, about the stability conditions, is that they form a space. So Bridgeland's theorem is that he wrote down a metric on the set of all stability conditions, and then he shows that this forgetful map that takes, this is whatever the category is C greater than phi comma Z, and just keeps the homomorphism Z. And this map is a local homeomorphism. And then in a project with my student, Alekos Robotis, we were constructing a partial compactification of this space called the space of augmented stability conditions. And this is, I just show you a picture of what it looks like in the case of P1. So what ends up happening is that the augmented stability condition space, we introduced it as a tool for studying semi-orthogonal decompositions of the category C. And in particular, when you have a semi-orthogonal decomposition, so this is on P1. This is a sort of illustration on P1. So on P1, you have these Bailenson collections, and whenever you have something like that, that gives you a way to glue stability conditions and from each of the semi-orthogonal factors onto the whole category. And so in this case, having an exceptional collection gives you lots of stability conditions, and that allows you to probe some neighborhood of infinity in the stability manifold. And likewise, if you mutate the semi-orthogonal decomposition, or you take this mutated exceptional collection, you can probe some other point. And so the real crux of this project was, what about this point? What happens there? So at that point, you can sort of probe that point from this direction, or you can probe that point for that direction. And so the conjecture that it's a manifold with corners is basically saying that there should be some stuff in between here. And in the case of P1, it's slope stability. But in general, we have these two glued regions, and you can take the same limit point on the boundary, and we don't know that a neighborhood of that limit point is even connected. And in fact, if these admissible boundary points always have connected neighborhoods, that actually always, for any smooth and proper C, that implies the mass-Hom inequality. So the place that this inequality actually came from is the desire. We worked really hard for like 2 years to try to define this space, and then we couldn't prove that it was a manifold with corners. That was what we were trying to do. And so we just kept trying to prove it. And then I realized that it would have this implication that if the neighborhood of this point and these points at infinity were always connected, then you'd have this mass-Hom bound, and then you get moduli spaces. And then I gave up trying to prove it, and I just stated as a conjecture, because it turns out this mass-Hom bound is a very, very powerful thing. So we conjecture that the mass-Hom bound holds for any stability condition on C, on a smooth and proper category. And if it doesn't, then maybe we should add that to the definition and just consider a stability condition to have this mass-Hom bound. I want to say we're not the first people to study the mass-Hom bound. So the inequality, it was like considered basically people who are studying the entropy of autoequivalences of categories. So that's defined in terms of the growth rate of Homs between a generator. And so this mass-Hom inequality allows you to compare that to the growth rate of mass of objects. So this kind of inequality did appear in this work before, but I think in this project with Alekos, we noticed that this actually maybe should play a central role in the theory of stability conditions. So it has classical analogs as well. So if you take a category like dB-co of a Riemann surface, then this mass-Hom bound are these, basically it's a bound on the dimension of the space of sections of a semi-stable vector bundle in terms of the characteristic classes of that vector bundle. So this is a very classical thing that actually is involved in constructing Giesecker moduli spaces of Giesecker semi-stable sheaves. This is a different way of seeing it, although, yeah. And in terms of the properties of this mass-Hom bound, so if you deform the stability condition, that doesn't change whether or not the mass-Hom bound holds. And it also holds whenever you have a stability condition whose heart is Artinian. So those are like stability conditions coming from a full exceptional collection. And it's also preserved by gluing along semi-orthogonal decomposition. So using these properties, you can find many examples. And in particular, if you put those together, you can show that all of the stability conditions that we know how to construct on P2 actually satisfy a mass-Hom bound, because there's one that comes from the full exceptional collection, and then there are these others that correspond to semi-stable torsion-free sheaves. So this actually sort of gives a different proof of a different construction of the moduli space of torsion-free sheaves on P2. It's an argument for boundedness that goes through derived algebraic geometry and avoids some of the classical stuff. Okay. Now I want to tell you about mirror symmetry. So the reason I find this interesting, one reason I find this interesting is because basically returning to the Toa-Navaki idea of constructing mirrors as moduli space of objects in Fukai categories. So you have this little lemma. This is not a it's not a deep lemma, but basically if you have a Calabi-Yau 3 category and you find a class in the charge lattice in a phase such that the objects, the semi-stable objects in that class have some conditions. Yeah. So in other words, stable is equal to semi-stable, and you have some orthogonality between non-equal semi-stable objects. Actually, then the moduli space of objects that we construct is a compact Calabi-Yau 3 manifold. And the nice thing about this construction is you automatically get a Fourier Mukai kernel that relates the Fukai category and this moduli space. So in other words, in this case, it defines an equivalence between some category of twisted perfect complexes on this moduli space and the original category C. So this isn't specific to Fukai categories, it's just a general principle. If you have a stability condition, it gives you a source of moduli spaces that you can compare your category to the category of perfect sheaves, perfect complexes on those different moduli spaces. And under nice hypotheses, it's actually equivalent to it. Although one mystery I have to say for this approach is that for CY3 category, the moduli spaces have virtual dimension 0. And so they have no right to exist. And yet we know that there are families of sheaves on Calabi-Yau manifolds, so it's a little bit of an odd mystery. I would love to hear a like conceptual reason why, what would force a moduli space to exist like this, even though it should be 0-dimensional. Okay, so now I'd like to translate into symplectic topology. What this all says, because I think it leads to something interesting that's relatively concrete, like a question that symplectic topologists might be able to think about. So I'll stick with it, start with a Calabi-Yau manifold, complex dimension n. Oops, I get a lowercase omega for that was supposed to be an uppercase omega for the holomorphic volume form. So the objects of the Fukai category there are different proposals for this. I was reading up on this when as I was preparing for the talk. But but I guess I would like to consider compact immersed Lagrangian brains. So they have all of this data, they're unobstructed, and they have all this data that you need to define an object of the Fukaya category, but I'm allowing them to be immersed. And there are, I think the consensus is that, you should also probably consider certain singular Lagrangians and so forth, but I'm not sure that that's the case actually.
Is it clear to be close to making triangles? Because morphisms are linear combination.
Yeah, I think so. Yeah, I think that if you use immersed, I think it's already, you don't have to do twisted complexes. If you use immersed, so this is an observation of Joyce, basically. If you work with immersed Lagrangians, you don't have to do twisted complexes. It's already kind of a triangulated category. And then if it has a stability condition, then it's already idempotent complete. So actually, if you're able to construct, if you just start with immersed and you construct a stability condition, you don't actually have to include any more objects.
No, you have to include complexes unless you're doing graded connection.
Yeah. Sheets.
Yeah, I mean, if you do graded connection, then.
Okay. Well, I don't know what you mean by that, but let me, I only have a few minutes, so let me just say what yeah. I mean, the Lagrangians are graded. That's actually a key part of this, is that there's a grading function such that the holomorphic volume form restricted to the Lagrangian is e to the I theta L times the volume form on the Lagrangian coming from the Kähler metric on M. And so basically, you think of that, say that the Lagrangian is almost calibrated if this grading function theta takes values only in some interval, some small interval. And also, because it's not even known that the Fukaya category is non-empty in general, I'm going to also assume that you have a collection of Lagrangians that generate. So that's the setup. Now, in this context, there's this Thomas-Yao-Joyce proposal, which is an old proposal, precedes the definition of stability conditions in some sense. But the conjecture is that there is a stability condition on the Fukaya category where the following holds. So the category of things with the phase interval AB, those are just the objects that can be represented by a Lagrangian brain whose grading function lies in that interval. And I'm including in that A or B is infinity. And the central charge is just supposed to be the integral of the Lagrangian. And so the one thing that I mentioned, the sluicing thing, is that all you need are T structures and a central charge that satisfies certain inequalities. The Harder-Nara Simon filtrations are then automatic. They follow from the support property. And so in this symplectic context, it seems like maybe this is simpler than the traditional approach to this. So the traditional Joyce-Thomas-Yao approach is to try to really hard to describe what are the Harder-Nara Simon filtrations by studying the mean curvature flow of Lagrangians. And that's very interesting from a differential geometry perspective. If you're interested in minimal Lagrangians, then this gives you some way to think about that using category theory. But if you're a category theorist and you want to just construct a stability condition on the Fukaya category, actually all of that stuff is not necessary. You don't need to study mean curvature flow to get a stability condition. All you have to show is that these are T structures, which is also a hard differential geometry problem. But you also have to, so basically, if you interpret the general yoga in this context, then this is what you get. So basically, let's fix a reference Lagrangian and some W that's between 0 and 1, and you fix a norm on the nth homologic manifold, and then the conjecture should be that there's a constant such that for every W almost calibrated L, there's a lower bound on the volume coming from the homology class of Lagrangian, and that's sort of equivalent to the support property for the central charge. And there's an upper bound on the floor homology from L prime to any other almost calibrated L in terms of the volume of L. And this is the mass-Hom bound. So these are, these kinds of inequalities are things that people study in differential geometry. I've never studied them before, but I think that this is a reasonable starting point for the program of constructing these two conjectures are reasonable starting points for the program of constructing stability conditions on Fukaya categories, because they don't involve any mean curvature flow, at least not visibly. So, and then this is just the other comment that if those inequalities hold, and you can prove this other thing, which is that, and if actually for any two phases, all you have to do is show that there's an exact triangle like this with one grading function above pi phi I and the other grading function below pi phi I, then actually you just get a stability condition for free. So this is some proposal that instead of considering Lagrangian mean curvature flow, maybe there's another kind of surgery where if you take the grading function and you want to cut off at a certain value, and you could maybe use that to do some kind of surgery to break L into L1 and L2 with these properties. So it's a slightly different question, which might be easier to approach than the mean curvature flow. Yeah, and once you do this, you get the stability condition. So the thing I want to return to at the very end is this question about what is homological mirror symmetry. This is the motivation that I started with. So this is just the sort of cartoon proposal. But this, based on everything I've said, this is a more concrete proposal. So first, step one, so you start with a Calabi-Yau manifold. And step one is to verify these inequalities, just a specific thing for this Calabi-Yau manifold. Then to show that every Lagrangian, you can do a surgery to break it into pieces with grading function bigger than phi and less than phi for two values of phi, as in the lemma. And finally, just find a single embedded special Lagrangian torus. And so, there's a lot of development on this with the methods of Yang and Li, and that, but my sense, most of my knowledge of this is based on discussions with Dan Pomerlano, who's a friend of mine who's really an expert in this stuff. But the sense that I get is that, you can construct special Lagrangian tori, but it still is out of reach to construct actual special Lagrangian torus vibrations in any kind of generality. So the advantage of this approach is that you just need one special Lagrangian torus that's going to be a semi-stable object in the Fukaya category. And that tells you, and now that gives you 1 point on your moduli space. And then if you have this other structure, then you use the stability condition to get the whole moduli space. And again, the advantage of this approach is that once you have the moduli space, which is given to you by the machinery of algebraic geometry, you have an automatic comparison functor coming from the Fourier-Mukai kernel. And so now the question is phi an equivalence? So, okay, this is not an easy program to follow, but I think the idea is that there's sort of a hierarchy of conjectures, and the deepest, the most profound conjectures, well, you could say, how hard is this conjecture to falsify? And so the conjecture that there is a mirror and that the category is equivalent is you'd have to show that there is no mirror, and that all possible Calabi-Yaus, the category is not equivalent, is very hard to falsify. And so I think the idea of this construction is to bring this down to a statement. You can actually make it on a manifold by manifold basis. So for every m, you can just check, does mirror symmetry hold? It's now a yes or no question. And the yes or no question are still hard questions in geometric analysis, but at least it's a yes or no question. And I hesitate to, probably this functor is not always equivalence. Probably it's fully faithful or something like that, when you can get the 1 through 3 to work. But it's, I think it's too much to hope for in general that it's equivalence. In general, C is like some kind of non-commutative resolution of this moduli space. So basically, when the space has singularities, you're out of luck. Okay, the last thing I just want to say, that's the end of the talk, but I also wanted to give a plug to this journal Moduli. It's a new journal, and we are currently getting lots of really great submissions in algebraic geometry and related fields But because this is kind of a mixed audience, I just wanted to advertise that we would love to involve moduli theory from all different perspectives, and symplectic and differential geometric, et cetera. So consider us. Okay, thank you.